Okay, we're live.
Okay, I am Julio Leão. I am the director of Ensilica Brazil, and I would like to thank you first, Fernanda, for organizing this presentation for you guys here at URGS and the people who are online. I would like to thank to Mateus for doing the transmission and recording this presentation if someone wants to look at it later. And I would like to introduce you to Davide Sarta. He is the VP of Engineering, of SoC Engineering at Ensilica. He will do his proper introduction soon in a bit. And we plan a 1 hour presentation, 1 hour and 15.
Probably more, yes.
And that's it.
Okay.
It's yours.
Thank you, Julio. Yes, thanks for the hospitality here. Nice to be in Porto Alegre for my second time. I was told that it's called Forno Alegre, if I'm not wrong, because it's very hot. Actually, it's not that hot. It's very nice temperature, nice weather, and nice people, I must say. So, okay, let me start. It's going to take probably a bit more than 1 hour, like 1 hour and a half. So hopefully you'll be patient and it will be useful as much as possible. So this is the agenda. I will go through a small presentation of Ensilica first as a company. So who we are, what we do. But it will not take long. A few slides, I will be very fast because I want to move into the interesting bits, technical bit, which is silicon design flow from the start to the end. I will particularly emphasize the problems that you have in designing a large system on chip, which are different from designing a small microcontroller. And you have to do things in a certain way, otherwise it would be very difficult to reach a stage where you can tape out. I don't know exactly your background. Tape out is the terminology for releasing the masks to the fab and start the manufacturing process. And I will try to explain why. So that would be system architecture, SoC architecture. And then there is a section where I would like to stress the importance of IP reuse. I will try to do it in a context which is also slightly commercial. So make the hypothesis that you want to start a startup, for example. You have an idea, you have a concept in mind, and you have to develop an ASIC, a system on chip. What is it that you have to do? Where do you start? Because you just have the idea. Do you want to do everything yourself, or do you want to go step by step? So I will try to highlight pros and cons of doing that, and what are the first steps you have to go through to size the cost of your idea. And then I would like to give you a view of the silicon job market at the moment, where we are. By job market, I really mean how many people, what kind of profile, and where we are worldwide, not just Brazil or Europe. Do we need silicon designers? There is a shortage. There is no shortage. What is the future? Where we are? Projections. That's the argument there. Yeah, and then if there is time, hopefully I will try to have at least 10 minutes for Q&A. I would like to be as interactive as possible. So if you want to, if you really feel like you are not understanding, feel free to ask a question now or perhaps at the end of the presentation, as you prefer. Okay, yeah, that is me. So I'm responsible for the SoC, the digital SoC organization in Ensilica. Basically, we are together with recruiting, developing. It's not very hands-on, but I'm still quite technical in my management action, let's say, in following what happens onto the many projects that my team executes. I will explain what are those projects in a minute. I'm based in Bristol, in the United Kingdom. As you may hear from my accent, I'm not English, I'm Italian. So that's, I've spent a long time in Italy, of which 4 years in STMicroelectronics Catania. Then moved to Bristol, still in ST for a long time. Then Imagination Technologies, Blu Wireless, a 5G startup in Bristol, prior to moving to Ensilica in 2022, so 2.5 years ago. My background is mostly technical background, is functional verification, architecture, SoC architecture in particular, before moving into project management and then team management now 10 years ago. Okay, so just a few words on Ensilica. Started in 2001 as a small company, just 3 people, doing just front-end digital design services, FPGA to ASIC, not much at that point, but it quickly increased in the first 10 years to do almost the full SoC design flow. Then published a presentation, the team acquired analog design capability, then functional set moved into automotive, which requires special processes in place. Acquired the Sheffield, which is a city in northern England. Acquired the Brazil team in 2021. That's the starting of a very nice adventure in Brazil. So nice that we just expanded it not a long time ago in 2024, I think October or so, in Campinas.
I'm sorry, could you just
Sure.
check on height there? Someone asked. From someone from the audience.
What do I have to
Just
do?
click height there.
This one here.
There
Okay.
you go.
Right. Okay. No problem. It's a public company, so it's in the stock market in London Stock Exchange since 2022. The size at the moment is 176. That is probably 2024. I think we are approaching 200 now, and we are increasing as an organization. Yeah, these are the locations, as you can see. Oxford are the headquarters, Bristol, Sheffield, for presence in Germany. Design, RTL design or verification, and we stop at the tape-up point, and at that point, the customer will continue with the following the rest of the process, including the mass production. So it's only providing the development service. We do have several IPs. I will not mention them all, but I will say the quantum computing in particular, or the cryptography in general, the quantum computing. I don't know if you know this, but basically, what we mean by quantum cryptography is new kind of cryptography which is resistant to quantum computing attacks. We are all at risk. Quantum computing, if it becomes successful, which it will be at some point, it is to an extent, all the algorithms for encryption of credit card and banks and so on are at risk. So the algorithms themselves have to change to be resilient to those attacks. And this is called quantum cryptography. So we have several IPs, Kyber, Lithium. Some of this designed in Porto Alegre, by the way, by guys here, that we offer to the customers. Okay, and in terms of markets, it's quite a wide range. From automotive, that is, we've been quite active and successful in this application field. Sensors and control, automation, factory automation. Yeah, you can see, you can read many of the fields there to RF and comms. So satellite communication in particular is an area where we have developed a lot of knowledge, reputation in the market. We have taped out important devices in the past 2 years, and that is including satellite communication in 5G spectrum. And healthcare is the last one. So we are active into many different areas. And it's almost, I would say, almost no limit to the kind of chips we can design. And in terms of application. Then in terms of what services we can do, you can see a snapshot of the various the various activity we can support, from having a lab to do the system design to the digital front end and so on. So each site, there is a list of those sites here. I have a specialization. The headquarters, of course, cover everything. Bristol is more digital. Sheffield is more analog. Bangalore is mostly digital verification with a bit of front end. Porto Alegre is expanding, does DFT, and together with Campinas, as you can see, if you add the last two rows, it's pretty much covering all the aspects. Over time, the intention is to have fully autonomous sites capable of doing an entire SoC, pretty much everything. A few examples of Ensilica's success in terms of technology: 7 nanometer, 6 nanometer, I should say, 12 nanometer large device. These pictures are not on scale, of course. I mean, the 7 nanometer one should be gigantic, and the one on the bottom right should be tiny. But just to give you an idea about the complexity. Complexity is not just size. Sometimes you have a small device in an old technology like 180 nanometer BCD, and that is more complex than a large device because you have to be extremely low power, perhaps, so very, very small. So you have other kind of challenges. And this is just an idea about end-to-end turnkey capabilities. So basically, it's telling you that we support the entire stack from system architecture, which I would like to explain what it is in a second, to the final qualification. And because we have both digital and analog, you can see some separation in this picture here. So like the digital path and the analog path, the DFT is for both. Then usually logical and physical implementation is done, digital is done differently from analog, which is custom layout. Then physical tape out, verification and tape out, and then the rest of the off-chip, off-die activities, so packaging testing and so on. So that's an idea about what we do and where we are. Let's dive into this bit of a complex. Thanks for that. That was a good one. Yeah, very noisy. So this is just trying to capture the entire flow from the beginning of the concept, let's say, of your ASIC, to, it's not really the end, because after validation you still have other, but it's we are focusing on the design aspects at the moment. This is a little bit more biased on digital. Analog is slightly different, so have in mind digital SoC for now. So basically, you have an idea, you have a technical marketing, let's say organization, or maybe it's just one guy. So you have to prove that your idea makes sense, first of all, right? You do an investigation, you know what else is available in the market, you do what is called marketing analysis, and you come up with a list of high-level requirements. It might be short, it might be very long, but that's what it is at that point. So it's just telling you what you want, but not how. The next step is called system architecture. So these two words are used so widely that have lost a bit of meaning. So what is system? What is architecture? So in this context, what we are trying to say is all those actions that translate the what into a bit of a how, or put a frame into the what, if you see what I mean. So it's trying to do the partitioning of hardware and software. So that is probably one of the first things you have to do. So you have to run an analysis of your problem, of the complexity of the problem, and understand whether you want to do this algorithm in a piece of software running on a CPU, or you want to do it in a dedicated piece of silicon, in an accelerator, in an IP, and whatever. Before you do this, of course, you have to partition your entire system, your board, into several chips. So I'm assuming this has already been done. Now we are focusing on that chip. So you want to develop that chip. This is chip design. How do you structure your chip? Because there is an easy solution, which is you put like a CPU farm and interface to capture the data, and then you put the data into a memory, and then the CPUs will do literally everything. And then the only one thing that you need is whatever interface to stream everything out. Is that an acceptable solution? It's extremely power hungry when you do this. It's likely to be very big. And the complexity of the software is something also to be appreciated and controlled. So this is not just an extreme example to give you an idea. But on the opposite side of the stream, you may decide, okay, I don't want any software at all. I want everything to be custom in logic. You design gigantic piece of RTL, you synthesize everything, and you still have interfaces for in and out, but the processing is done fully custom. And there is almost no software running because there is not even a CPU. That is the other side of the spectrum. In reality, we are always in between those two extremes. So there is what is called hardware-software partitioning, which is exactly this action here, deciding how you want to partition a problem and what you map to hardware and to software. You have to define the use cases as well. You want to have an idea about what external IPs you want to procure. So you don't want to design everything yourself. You want to procure procurement, buying, purchasing. Like a DDR controller, there's no point in designing one. You buy one from major vendors, there are many. You have to do a performance analysis, because once you have decided a sketch of your architecture, then you have to make sure that you have selected the right IPs. For example, is the right DDR the right bandwidth, the right clock? Is it DDR3, DDR4, PCI 3, PCI 4? You have to decide this, and it's performance, power, area. These are the three main things you have to keep under control continuously. So that phase is extremely important because it's like putting a frame into a painting. So now you know what kind of problem you have. You still haven't done what is called SoC microarchitecture, because all those major IPs will have to be done wired together, assembled in an SoC. So there are many other things that have to be decided. So you have to keep the die size under control. So you try to be very accurate in that. You now introduce the geometry. Geometry, I mean the geometrical aspect. So, okay, I got the diagram here, but where will the IP sit into the floor plan? How do we combine? So you try to do what is called a paper floor plan, which is literally sometimes even a PowerPoint slide with the size of the blocks, or the major blocks, representative. There are more sophisticated ways of doing this, but it's very important that you do it this way. So you start introducing the physical aspects of your die as soon as possible. You don't wait. You don't have to wait. And this is one of the key messages, actually. Never wait until you have the full RTL assembled and verified to understand how that will translate into a layout. You have to have that in mind already. It's called the paper floor plan. You start doing a boot architecture. So this is not something that system architects will care about. So the system has to boot. That's what they will tell you. But you have to define exactly how, from which external or internal memory. Do you want a boot ROM? Do you want an external flash to do the booting? Or is your CPU slave or some other agent which is off chip, which will download the bootstrap internally, and then after that you start. So there are many different ways of booting a system, and that's why it deserves an entire section. So once that is decided, power architecture. So that has to be kept under control again. So you have to have, so this is two things actually. It's a power estimation that will keep the estimation of your power always under control. You have to make sure that you hit the technical requirements and the system architecture requirements. So you cannot exceed in power. So continuously update your power estimation spreadsheet. But you also have to define your power architecture, which means which blocks will be active, which blocks you shut down or decrease in voltage and so on. So if you have concerns about the power, you have to decide at this point. Moving on, reset, clock, and debug architecture again. So this is another aspect that will start shaping the inside of your, so you haven't done any RTL coding at this point, just to be clear. That would be the next step. At the moment, it's all specification, spreadsheet, decisions, meetings, a lot of meetings to make sure you don't lose control of your main targets. And then you start defining specifying the blocks and the subsystems. You have to have a full list of IPs. The IPs that the system architects may have defined might be the major ones. Here you want to have a full list of all the IPs that you need to build your entire SoC. You may have to assemble those IPs in what are called subsystems, which are sort of functional clusters that you have to verify independently. And then there is the big thing of the interconnect requirement. The assembling a complex system on chip is not simple. The assembly process in reality means designing an interconnect, which is a network in the end. So this requires a lot of specialization and time. At this point, you don't do the
There you go.
just this? Is
Yeah,
it? Okay.
I think it's
Good.
I was just aligning the camera.
I see. Okay.
We can see your
Yeah.
face now.
I'm not sure it's a good idea, but yeah, that's fine. Okay, so yeah, at this point you define the requirements. You don't design the interconnect. But that means definition of how many initiators you have in your NOC, in your interconnect, what kind of technology you want, because there are different interconnects. There's network on chip, there are crossbar technology. You have to decide that as well. How many targets you have, what are the performance requirements for each initiator to target couple. Bandwidth and latency has to be specified. So you define basically all the ingredients that would allow a designer to then design an interconnect. So this is done at this stage. And you define then the patching and your ball out for the package as well. Once you have all the IPs in your hands, you know the interfaces, you start creating a spreadsheet with a list of pads and balls. That's the SoC architecture. Front-end design is then writing detailed specification and doing basically all the rest. Design, the assembling of all the IPs together, the connectivity of the connections within them, the design of the interconnect I mentioned before. There is an important step, which is lint CDC RDC. So before you move into functional verification, you want to do some static verification to sanitize your RTL. So you run it through lint, you make sure there are no the clock domains are well crossed. That is called CDC. Similar for RDC, which is reset domain crossing. If it's designed with power islands, some many are that way, then you have to design the UPF, which is exactly telling the verification people which islands, power islands are on and off, how they transition from one to the other one, and which power goes to one part of your SoC and which one goes to the other part of the SoC. So the UPF design can only happen if somebody has written a power architecture, which is the previous step. So then you design the UPF, and the next step, the SDC, timing constraints. So of course, we are not designing software here, we are designing hardware, which has to work at a certain frequency. So somebody has to tell exactly what is the frequency, what are the constraints on the IOs, and so on. You do a light synthesis before you hand over your RTL to the next step, which I will mention, implementation basically. You do a light front-end synthesis to make sure that there is a chance to achieve your final speed. You may want to design a block at 1 gigahertz. That is not simple. Depending on the technology, it might not be an easy thing to do. So you run a quick synthesis, no DFT, no physical awareness, very, let's say, light, and look at the results. If they are not, they're under control, you don't need to close timing. So if there are violations, that's fine. But if you find that is achieving like 500 megahertz and the target was 1 gigahertz, there is no point in starting implementation. Something is wrong with your RTL. Look at it, start again, analyze the critical path. Perhaps you may even conclude that there is a massive problem that you cannot solve. So you have to go back to the SoC architect and tell me, the problem you gave me is unsolvable. We have to do something here. So it's an important step. And you do the power analysis as well. So the power, again, the idea is always the same. You keep die size and power reviewed and improved in accuracy throughout the flow. So the power analysis, now you have the RTL in place, so you can use tools to analyze the power consumption a bit more accurately. course, power consumption depends on switching activity, so you need to have some rudimental. Either you have some software already, some verification, or you make let's say an assumption on switching activity that you may have in your design. So that is a difficult one to do, but usually 10%, 20%, you assume that all the nets within your net is your design, or the primary nodes of your design will switch at that frequency, at that probability with respect to the clock. And that will give you a rudimental idea of your overall dynamic power. And you can also have an idea about the leakage that your block or your SoC will consume. And again, doesn't need to be precise. It cannot be precise at this stage. You haven't done any layout. But if it's within the range of accuracy that it would be like plus minus 25%. If it's within that, then it's fine. If it's well over that, there is a massive problem. So you go back to SoC architecture immediately. And then you may even go back up to the technical marketing theory, because the idea is to not go back more than one step. Okay, so if every single step is done well, you don't go back up to the top of the chain. That would be a massive problem, because of course you have to imagine that there is an entire team that has been working now. Going back to the marketing stage means talking to either the customer or the sales and marketing guys and having to tell them, okay, sorry, but the idea doesn't work here. They have already maybe engaged with customers. They may even sign contracts and so on. So it shouldn't happen. That's why every single step has to be done with good care before you start spending too much time, which means too much money, and have to go back. So the sooner you can anticipate the problems, the better. And this is particularly true in large SoC, where the team you have to involve is much bigger. So you spend much more money. Sometimes you have 50, 60, up to 100 people easily working on an SoC. That is a machine that work and work. If he has to stop and go back, that is a massive problem financially as well. So things have to be done in a certain sequence, and try to limit the amount of loopbacks. Next step, functional verification. Now you have to check that everything works as expected, as the spec. The rest is the usual implementation flow. I will not say too much onto those 3 steps because of time limits. Of course, it's fundamental steps and not simple at all. Things have changed in the industry. I would say there is a high level of specialization everywhere here. So usually we don't have guys who are able to do everything. So there are people who are implementation people, others who are functional verification guys, others who are RTL designers. It is good that they have an experience in the other side and the other things, but there is a requirement for specializing your function because things are really, really complicated. I haven't talked about software, but at the point where you define a system here and you do the hardware-software partitioning, you move some of the complexity onto the hardware. I'm highlighting the hardware onto the software. I'm highlighting the hardware part here. Chip signing off is the final stage where you have to close timing. So when you do implementation of place and route, the algorithms used to assess timing, for instance, or even physical, are not precise. So they do whatever they can do because they have another problem to solve, which is layout. So there are other tools which are specific for checking timing violation, physical violation, rail, power consumption, and so on, which are called sign-off tools. So that is the final step. If you find violations you cannot fix, you have to go back to place and route. And there is a loop here that is run several times until you are clean in sign-off. Of course, there is a correlation that has to happen between the layout tool and the sign-off tool. Want to make sure that they almost say the same things. Otherwise, you will have big violations in sign-off that you don't see in place and route. So that shouldn't happen. So you have to fix that as soon as possible. Usually you don't go back to synthesis. But again, that could happen. For significant violations, you may have to request a new synthesis, perhaps because you underestimated or you haven't considered the flow plan well, and therefore the synthesis was run with a different flow plan, things like this. But we try not to go back to synthesis as much as possible. There is something missing here in this picture. Any idea? An important step that is not in, it's not in the picture. It should be in the bottom there, but. Right, who said that? Good, DFT. Well done. Yeah. The reason why it's sketched that way is, like a single thing, because if you want, at the top, what you have is the functional path. You always have to keep in mind that what you design has to be tested. So there is an entire activity called design for testing, which has to start as soon as possible. The larger is the design, the more important is the testing. So you have to make decisions as soon as possible about codec strategy, how many compressors you need. You want to use at speed testing, isolation wrapping. I mean, the list is very long, to be honest. It's a highly specialized function. Once that is done, you start doing the DFT specification, so very detailed about how many scan in, scan out you want, and many other things. So that is a complex function. Usually is given to experts in the field. There's a big shortage of DFT engineers in the world, I can tell you. So for some reason, people don't want to do DFT. I suppose it's because they found a little bit more sexy to do the functional path. I can tell you there is a lot of intellectual effort in doing DFT, and in the end, that gives, if you want, the motivation to do things. There are complex problems to solve, which are non-functional. But what is a function in the end? Everything is a function, including DFT is functional in its own way. Anyway, that's the situation. There are not many DFT engineers, which in a law of the demand and offer has a nice consequence that you can imagine. So, shortage of DFT engineers, the ones who can do DFT engineering are well paid. It's the way it is. Okay, the bit you can see on the top is the leadership team. It's better if I take control of time. Yes, there are 4 key people that are always present. One is the SoC microarchitect, the one who leads the SoC microarchitecture part, and he's also the front-end lead as well. So he's a front-end expert normally. And then you have a lead for verification, a lead for DFT, and a lead for physical design. This is a typical leadership team you have in every project. Of course, you need a project manager. And normally you also have a program manager, because Silicon is part of the story. You have also software, you have the package, you have the testing on the package, you have the PCB that you have to design as well. So there are many different functions which are usually coordinated by another level of management called program management. So you have that as well. Okay. So this is trying to highlight what is system architecture. So this is, again, assuming you have a concept in mind and you have done the marketing analysis, your technical investigation, your business case, what is the next step? Is the system architecture. So you define the use cases. Basically how many ways your chip can work. You identify the major IPs to procure. Which USB you want, which JST, there are many interfaces, but you have to identify not all the IPs, but the major ones, yes. The ones you have to buy, in particular, from third parties. Fix the performance targets, and you do static analysis. So this means, for instance, I made the example of a DDR. So you have to decide which DDR you want, how many instances, running at which frequencies. And that, how do you decide? Is it okay to have DDR 800 or DDR3, DDR4, and so on? Usually it's done with spreadsheets at the beginning, because don't forget, you don't have anything at this point. You don't have RTL. You cannot run simulation. So you are yourself and a piece of paper and a spreadsheet, basically. And typically, the higher you are in your chain, let's say the biggest are the consequences of your mistakes. So making a mistake at system architecture level is much worse than making a mistake in timing or layout. Fine. And also, you don't have many tools to check how good, how nice work you have done. So if you make a mistake in layout, timing analysis will tell you, physical verification will tell you, you'll fix it. At the point of architecture, you don't have that. So you have to use a lot of your experience. So usually system architects are people who have worked for 20 years, and they use their experience to guide themselves into how things should be done. Okay, so I think I mentioned that already, that we are still working on what the system should do. That's system architecture, but while the MRD defines exactly what the system architecture creates a frame around the what, and basically the technical constraints into the next phase, which is the SoC microarchitecture. So here, based on MRD system architecture, the SoC microarchitects developed the microarchitecture of the ASIC. So this is now exactly saying how we do it. I think I've already listed most of those phases. I will not go back to them, but each one of them is always present. I haven't mentioned security architecture. That depends on the kind of design you do, but it's an entire long section in your microarchitecture document that deserves attention at this stage. Large devices, why they are different? You have to accept that there are limitations in the ability of implementation tools in particular to deal with large devices. You cannot give more than 3-4 million instances to a place and route tool. It doesn't work. It will never converge. And we have to deal with chips that usually have 20 millions, 30 millions, 100 millions instances. We're not talking about gates, we're talking about how many instances in your layout. So to deal with that level of complexity, you need to partition your design. So you have to use what is called hierarchical flow. And this is not just in place and route, in the end is in dealing with a high level of complexity. So everything will have to be done with different level of hierarchies that are then combined together. It's done in front end because you identify the subsystems, the functional cluster that you verify independently. It's done in backend because of the limitation I mentioned, and it's done in DFT as well, because you develop isolation wrappers, which inside that DFT compressors. Basically, you deal with that level of complexity in a similar way with the hierarchical levels. Yes, I will skip the second point, it's not particularly important. But one thing I will mention is it's key to identify, to capture the hierarchy of your backend directly into your front end. So that means if you identify a physical partition and you say, okay, these IPs together will be nice if they are placed here. You want to preserve that position when you assemble your IPs together. Because if you don't, then when you try to map, let's assume you have defined a subsystem collating IPs which have nothing to do with each other, and basically one will have to be, then one is too big and cannot be placed there. So when you move into the backend, so you will have, for that subsystem, IPs here, and the other one will have to stay back here. So that level of hierarchy doesn't work. It will have to be either removed, or you have to use other techniques to then do a fit through those subsystems. or the opposite. Perhaps you make a mistake and you take the subsystem you assembled in front end, move it to back end, and you put it in a point in your floor plan where you then realize that actually the IPs this subsystem have to talk to are on the opposite side of your floor plan. And that means having massive timing violation that you only realize when you do the top level timing analysis. But that is, if you remember the previous flow, it's very late. So you have now designed your front-end hierarchy with certain decisions for subsystems. You have converted those subsystems into physical partitions. They've been placed, and now you realize that this partition here is talking to that partition over there and is crossing the whole device, very large. There is no way you can converge timing anymore. So when you create subsystems, you have to know where they will go into your subsystem. You have to know immediately. Of course, the subsystem is a level of hierarchy that you use to do functional verification. So you have, this is the triangle you have to explore. So the functional verification lead has to talk to the front-end designer, who has to talk to the implementation lead and decide together how to create your physical partition subsystems. One will say, no, I want this IP to be here in my subsystem because otherwise it would be very difficult to verify the subsystem. It's important. The other one will tell you, well, no, it doesn't make sense because I need that IP to be up there and so on. So it will introduce a geometrical constraint. So it's a bit of a challenge, but usually there is a way out and you reach an agreement there and you refine your floor plan to make everybody happy. But it's important that we do this in an iterative way. And this is how it's done. So thank you. You have a SoC architecture must be layout aware immediately. That's the concept here. So you don't define your SoC architecture just functionally. Think always about where things will go. The way to do it, you have your list of IPs. So this is, you do a first, let's say, functional diagram where you don't really care about where things are in a floor plan. You have an IP list, a list of all the ingredients, and you have the list of paths in your system as well. You do the die size assessment, and you start capturing the constraints coming from your PCB. So that will give you the frame. So the PCB, that's how it has to be. You want the DDR at the bottom. You want these interfaces on the right, on the left. So you start creating your frame. You design from the outside to the inside, basically. And once the frame is decided, and once you know the size of each block, because you have done a die size estimation, then you start doing your floor plan. And you iterate if the floor plan doesn't work. So that's the one, how to proceed. Block topology. So you have to design the interconnect. All those blocks will have to be talking to each other. Again, design your interconnect aware of your physical location of your blocks, because that's the only way it can work. Otherwise, if you decide that you have to go have a big connection from one place to the other one, and you haven't put the right topology of your block in place, you will have a lot of problems later on. So you can do this even on a piece of paper, honestly. There are tools that can assist you. But it needs to be done at the SoC architecture stage, so immediately. Clocking is the other one. You want to minimize the distance between the PLL generators and the endpoints. So again, once you have the floor plan, design your clocking architecture based on the final location of those IPs. Yeah. To keep the clock island area small, which means the clock jitter small. And that will help with timing. So don't have long paths going from the bottom of your chip to the opposite to clock a few flops up there. So think about this. Do the mapping. Perhaps increase the number of PLLs if you really need to, or change your floor plan eventually. Package selection. Of course, now you have the list of IPs, a list of IOs. You need to decide the power as well. So how many core power signals you need to give power to this chip. And that will give you an idea about the list of bolts. You have an idea about the power estimation. All the information together will allow you to select the package. It's important to do it as soon as possible because there is a cost associated to the package. And that is an important cost that you have to appreciate sooner rather than later. And it may lead to changes in your decision. Perhaps you will accept to remove one DDR interface because otherwise the package is too expensive. So it's about, without a DDR interface, I cannot do certain use cases. Otherwise, fine, I will give up on that feature, but at least I can use a smaller package. The sooner you know this, the better. You cannot wait until you have your die and then see where it will fit. Okay, so that's an overview of how things are done in a flow. How will it work normally in stages? So you probably know, I don't know, continuous integration that is used very often in software development. So it's highly iterative. We use Agile, for instance, Agile programming. We don't use this in silicon design. The reason is very simple. It's like when you build a building. Agile means refining the requirements continuously and adjusting your software. But you cannot decide to add a floor in a building after you have built already 10 floors because the foundations have been sized for 10 floors only. You cannot just add another one. In reality, the problem with silicon design is that it's such an expensive and long process in implementation that you want to know what you are dealing with sooner rather than later. So you cannot just restart everything every 2 days. To do a layout, it will take even 2 weeks, 3 weeks. We have to do it many times, but in an agile programming model, that will have to be done hundreds of times. It will take infinite time. So you have to have much more stable requirements. Of course, it's also true that having perfectly stable requirements is not real. So what we have is a sort of a controlled agile, if you want. We go 4 release points. Basically, front end and back end are developed in what is called the incrementally quality controlled way. So first thing we release is, we call it pre-bronze, which is the definition phase. So it's exactly what I said at the beginning. So the guys getting together to define the chip and write spec. So that's what pre-bronze is. There is no RTL there, or very minimal. So that means in that diagram, front-end completeness is very low, and also the quality of your front-end is very low. There's no verification, pretty much. Then the next step is bronze, where you have introduced more design completeness and more quality. And silver, you have now with everything is being captured. So the design is complete, but the verification quality is still small. So basically you engage backend in parallel with frontend. You don't wait until you have fully verified your ASIC. That will take, so it's not sequential. You do it in parallel, but in a controlled way, because also you don't want to waste anybody's time, because backend is expensive, tool licenses are expensive, so you don't want to ask people to implement a block which is very immature. So it has to be done in a controlled way. And that's why we go maturity points with clear definitions. So this is very vague, but we know exactly what bronze means. So we have a list of criteria to label a release as bronze quality or silver quality. Okay, I will skip this. It's not particularly important. Just to make another point about DFT. What is more important, functionality or DFT? So you're designing a chip. What is more? So you may think, okay, what is really important is that it works, right? But when a chip doesn't work, what are the 2 main reasons why a chip doesn't work? One is because there is a bug. So it's a bug in the spec, a bug in the RTL, and you realize you discover that bug only when you validate your chip. The other reason is you have a manufacturing defect. So when you manufacture your device, the fab has introduced a mistake, a fault. Now, of course, both are very bad for the success of a program, but a bug perhaps is workaroundable. If you leave a fault, you can discuss, but in the end, validation and the finding functional bugs and finding workarounds can be done in one package. You don't need, when you have mass production, you have millions, you need one. You take one and try to find a workaround that you give it to a customer. When you have defects, then there are a few packages, a few parts that don't work. There is nothing you can do with it. So you have now delivered your faulty chip. It's been assembled, put on a board, put in a system, whatever the system is. Perhaps it's up in a satellite or whatever, and you discover that actually there is a fault. And there is nothing you can do. I mean, I cannot find an easy workaround there and so on. So this is called escapes. So basically, the FT is not strong enough and it hasn't detected certain manufacturing faults. I would say for mass production, the FT is as important as functional design. So it could damage the reputation of a company because when you have customer returns, it's a nightmare. So going into that loop where the customer will give you, this doesn't work, particularly if your device is in locations which are difficult to reach. So it can be expensive and so on. So you want to identify all the faults, manufacturing defects, as much as possible immediately. So you need to have a robust DFT. That is as important as functional design. So that's one point. That's why we have DFT as a primary function in our chip. So we need to identify. So we are building now an NRE cost. NRE means no recurrent. So basically the cost that you have for your development. We want to size it. We want to say, okay, somebody will tell you, okay, I got this idea here. How much do you think it will cost? That's the question. Okay, so you need to identify the man effort. How many people are needed for how long? EDA tools, third-party IPs. You need to procure IPs. Cost of the masks, cost of your package, cost of the validation, functional validation, and testing as well. So the combination of all 6 points will create the cost of your. There is more. Okay, I haven't considered software PCB design. In reality, there is more. Just trying to focus on the SoC really for now. But the others will have to be considered as well. Yes. So just 1 second about the man effort estimation. This is the major difference between the major difference between silicon development and software development. Is one of the two is no forgiving. In the end, when you develop RTL, you are writing software, right? So it's very long. It's another language. It's a special kind of software, but it is software. And there is software everywhere. You writing the scripts in Python to drive a tool. Everything is software, right? The major difference is if you find a software bug, you send a patch and you fix it. If you're designing an FPGA, you can burn and blow another FPGA, you can solve it that way. But when you define an ASIC and you find a bug, the cost, and I have a slide on what that means exactly, is quite significant. So because of this, it's important to reuse as much as possible silicon-proven solutions. That's one point. The second point is you might be under the impression that it is actually better to develop certain blocks yourself. So think about an SPI block. You talk to a vendor, they will give you a price. I said, wow, expensive. I can do it myself. It's not difficult. It's just an SPI. It will take me what? Let's put a calculation together. You will need definitely one designer for 3 months because that will include specification that you need to have. You need to write the RTL. You need to run all those checks, LIM, CDC. You need to run synthesis, then you have to do implementation trials, at least, even if it's just a software IP that we are considering here. Functional verification will have to be done at top quality. This is not software, this is hardware. It's not forgiving again. Now, Simple, $100K, including taxes and everything, just a round figure. It depends on where you are in your location. It might be even more, or it might be a bit less. The calculation is 50K for the people. Then you need EDA tools. That's usually quite expensive. In this case, there is no implementation. Usually it's the licenses for implementation, which are very expensive. Just another 10K. Total 60K. You can easily find an SPI for 10K. Sometimes it's even given for free, but that is special agreements. But much less than 60K for sure. And on top of that, you are now designing a new block, which is not silicon proven and may have a bug. Because how do you know? You can run as much verification as possible. You will always have a residual risk. So really, the conclusion is, focus your effort on your added value. So if you have an idea in mind, that's where you have to focus. Purchase all the rest as much as possible. There is a limit to this. You cannot purchase literally everything. But your effort should go into what makes your solution unique or advantageous. Yeah, okay, that's enough. Oh, that's a view of how many people are needed for an SoC. So this is like small, medium complexity. ASIC design is it's not like software. It doesn't, it's a long processing chain as we saw before. So it takes several people. Here is a small design. So I'm going up to 12 people, as you can see here. Different functions. You will engage implementation people a little bit later until you reach a point. Usually you have this peak here. This is where you have implementation, the entire verification team engaged, and so that's the peak. Then verification people will start disappearing, not all of them, because you also want to do gate level simulation, so some of them will stay in place, but they will go down, sign off, boom, tape out. That's the big decline. That's a typical shape of a resource profile, basically. Total execution effort, 10 man years. In this particular case, you can easily go to 30, 50, 100 man years. Just one example. This is just to say that in terms of, you got 10 man years as an effort. In terms of time, until you have your parts, that will take manufacturing time as well, right? It takes 3 months, 4 months until everything is produced and packaged. So it takes 1.5 years. Before that, usually it takes like 1 year of concept study, research, and so on. After that, you still have to do functional validation and so on. So until you go into a point where you can start earning money, you have recurrent revenues because your ASIC now sells in good volumes. It will take between, let's say, 4 years as a minimum. So that means you have to be financially strong to resist until these 4 years. And also don't forget that within those 4 years, the majority of your team will only be occupied for 1.5 years. And for the rest, they will be waiting for validation. So all the implementation guys, you don't need them anymore. And part of your verification guys as well, you need other people. But all your development, silicon development, you don't need them. What do you do with them? You have to do another chip, but that is other cost. So, and you have invested a lot of money already, and you haven't received anything. So you need good investors, basically, that's what I'm saying, that can understand with you that this is an expensive business, first. Second is, do you really want to grow a team yourself and then keep that team for 4, 5, 6 years? Or is it better to subcontract part of that development to somebody else, which may look more expensive if you compare it in that 1.5 years? But it would be much less if you do a proper comparison over 5 years, which is more realistic. So that's why there are a lot of design services companies in silicon design, because it's the business model that requires that. Yeah. At the same time, I don't want to discourage you. If you have any idea, It's an expensive business, but it's very lucrative. So if you have a good idea and your chip becomes successful, it is extremely lucrative, much more than anything else. You can get return on investment of a factor of 10, 100, 1,000. But it's also very risky. So I think the calculation is 10% of the startups will be successful, 90% will fail. That 10% become millionaire. Not me, but yeah, others. EDA tools, this is another important component, essential. It's a cost that will have to be considered because it's not insignificant. EDA tool providers can provide many different solutions, but in the end, in a way or another, it's a cost you have to take into account, not to be underestimated. Third-party IP cost, yes, shop around, negotiate on price. There are many IP providers offering a huge variety. When you receive several offers, prefer to spend a little bit more for something that you know works because it's silicon proven. Because again, it's better to. It's again an expensive business. The silicon provider, the EDA vendors, they will not give you EDA. Sorry, the IP providers, they accept no liability for mistakes. So if you go to Synopsys or Cadence and you buy, I don't know, a PCI Express model, and they will tell you after 1 year, sorry, there is a bug, and you have spent 1.5 million already. It's not that they will give you 1.5 million back. No, that's not the way it works. The liability is all on your side. The only thing on their side is the reputation, perhaps. It's not in their interest to give you something with a bug inside, but it does happen. And they will give you the fixed version for free, but you have to start again. So that's another many minutes. So that's the way it works, unfortunately. So when you have to select an IP vendor, go for the most robust, even if it costs you 10, 20% more than the other one, because it could cost you much, much more later. Masks, just to give you an idea, it's millions. So 20 nanometer, 1.x millions, 16, 12, 2.x, 7 nanometer, 9.x, and so on. If you go to 3 nanometer, honestly, I think we go into the 30 millions and so on. So somebody has to find the money for that. So it's not simple. Also consider that very often you cannot adopt a first-time success strategy because that would be too long. So you want to go fast to a first piece of silicon because, think about the situation. You want to show your investors, the markets, that your idea works. And maybe the FT is not ready, maybe the timing and so on, but you want to go as fast as possible because you have a demo milestone in mind. So usually what you do, you go tape out 1, quick and dirty, and then a tape out 2. So that cost has to be paid twice. Unless you can do an MPW, which is multi-product wafer, where you basically share the cost of your masks with other people. That is very effective because you go down from 1.x million to 100 million. So many people do this. However, if the chip is too big, there is no way you can do this because it does, the wafer has a size and the fab will not accept too big die because it's not in their interest. So if you have 150 square millimeter device, forget about having an MPW. So you have to pay the full masks twice. At that point, you want to consider first-time success at least, which means it's not 1 year of development. Then it becomes much more because you have to have verification at top quality, which means you have to have FPGA prototyping, emulation, all those techniques, which will add cost to your development. Emulation in particular is already millions to consider, to be considered. Silicon design flow. So if you have, as an idea, I have a good concept. I want to create a small team. You and your colleagues, perhaps. You need to have a flow in place because the EDA vendors will give you the fundamental tool, but then they have to be sort of educated with the scripts that you have to develop. Don't underestimate the complexity of these flows. So it's not just scripts, it's really an entire software package that you have to develop and will cost you time and effort. We made some analysis some time ago. It will go between 6 months and 2 years of time to develop a reliable design flow. And again, that's another reason for the success of design service companies, because they have this. Together with the people, the competence, and so on, they also have a robust flow. Which you, if you're creating a new startup, you have to do it yourself. So that leads to a final point on this topic. So you have this ambition. What do? You create a design center yourself, or you ask a service provider to work. Is the ambition of everybody. I mean, as myself as well, to create a design center because you want to do everything yourself. It's fine. I'm not saying that that's not a good idea. You have to consider the cost with the implications of that decision. You need to budget for the time to develop the scripts, the time to find the right people to help you. Time is money. You have to consider the cost of EDA tools. And then the fact that it takes 4 to 5 years until you finally get money. So you have assembled a team, and you cannot afford to keep the team occupied on another product because you're still waiting the first product to come back. So either you start considering redundancies, or you fire the people and so on, which then will be a problem for your company because you will not find people anymore if you have done that once. So one solution might be that you split the development in 2 sections. You do the front end, which is where your functionality makes sense. So you do the RTL design, and you do the simulation. That is not particularly expensive from an EDA tools point of view, because the simulations are not very expensive. And then the RTL to GDS, so the implementation, you offload it to a service provider. Many people do this, but it's up to you. You can decide a different trade-off. The other problem is this one here, the job market situation. So I mentioned at the beginning that I would talk about this. This is just a snippet from several articles, all from US, basically highlighting that in the semiconductor industry, there is a significant skilled labor shortage. Basically, we are not enough. And it's not just US, it's China, it's Europe, it's everywhere in the world. People have been interrogating themselves, well, why? I think, if you look at that graph, this is the popularity, the number of degrees of computer science over year. So from 1964 to, I think it's 2016. Computer science is much more popular than electrical engineering, which is going down. It's probably pulled by artificial intelligence. People are considering computer science because artificial intelligence is a hot topic. And we are starting to pay the price for that decision now, because that was the situation in 2014. Now we don't have enough engineers, because of course, even to do artificial intelligence, you need, in the end, silicon engineers. And you need them for anything else, which is not artificial intelligence, because you still need digital communication, automotive, there is no AI in there. So it's a consequence, and it is a problem, honestly. So to be honest, it's one of the reasons I'm here today, to also try to pass this message to you to the other people. I think we should do something in schools and universities. I'm doing my bit in England, trying to get people more excited about silicon design as much as possible. Because there is a need. On the other side of the story is, again, law of demand and offer. Because there are no many silicon designers, the salaries are going up. I don't know for how long. This is good news for all of us. I think there are, US, of course, is giving much higher salary than the rest of the world. to be honest, the cost of life is also much higher, so it has to be considered. But we are talking about 300K, 350K, dollars for an engineer with 10 years of experience. So that's the kind of madness we have reached already. In Europe is a bit less, but we are still going up and up, much higher than inflation, because there are no people available. In the end, you have a negotiating power when you have to, yeah. That's the situation there. I'm not sure for how long it will sustain, because at some point, usually, the job market will react. People will realize that it's actually a really good job, and they will start applying more. So, but over now in the next 5 years, I don't think the situation will change. Okay, I've almost finished. I think I've explained the whole design flow. This is basically the same kind of table in a vertical direction here, as opposed to the horizontal, which was before. It's the different kind of service we can offer as a company. And we are not unique. I mean, other companies do something similar. So there are a model where, yes, the customer does everything up to producing a net list, and we do the rest. Or to the opposite side, to the other side, where we do everything. So the customer does only the requirements. We do the system architecture, the microarchitecture, and everything else I talked about from the beginning. Usually, there is always like what is called a digital core. This is the concept. And normally, the customer wants to retain at least that major spatial IP. But, there are many examples of why that IP is spatial, but they want to keep the IP. So they give us the IP to us, just that unique IP, and we do everything else around that IP, and we do the SoC design, basically. Yes, this is just a selection of one of the most popular kind of working model. This is just examples. There are many other players. But the one vertical, what is called microarchitecture to GDS, is where the system is known by the customer. They do the hardware software partitioning, they shape everything, and they come to us with a very detailed system architecture. But they haven't done the microarchitecture yet, so that we will do that. And then we'll ask them to review and approve, and we do all the rest. So this is quite a typical working model. Okay, this is the last one. It's just one slide summarizing all the bullet points. Silicon development is a highly specialized, complex, and also expensive business. And it is much more than writing a piece of RTL that works, right? So it's much more. I would say that the architecture and microarchitecture phases, so that was I said at the beginning, these are the most important phases in the overall design flow. That doesn't mean that the others are simple or no, but if this is done well, the rest is not easy, but it's predictable. So you can more easily predict how long it will take. It will still be complex and challenging, but it is predictable. Unfortunately, there is no chance to become an SoC architect without solid experience. So we have to be honest. It takes at least 10 years of diversified experience. There are several paths to become an SoC architect. It's a nice job, honestly, because he's hands-on without, you see the system in operations, as opposed to just see a simple block. So you have that nice trade-off between being too much high up and seeing an abstract way of the system, or to the opposite, which is knowing everything about that little block, but not really appreciating what the whole SoC works. SoC architect is in between these two extremes, and I've been an SoC architect for many years. That's my totally biased opinion. Others will have a different opinion, I'm sure. But for sure, it takes time. So you need to have good, solid experience as a front-end designer, as an SoC verification as well. That's very useful because you see the entire SoC in operation and you develop a lot of experience that will be useful as an SoC architect. Bring physical awareness to specification. That's so as soon as possible. solid DFT for mass production. Don't leave it as an afterthought. Think about DFT immediately. Remember the cost of fresh spin is very high. Don't compromise on verification quality, never. Consider design flow, it's an important intellectual property. Remember the findings. So if you really want to define a design team for your startup idea and so on, remember that it's difficult to find good people, the right people. Okay, so it's not impossible. Okay, but it's something to take into account. Reuse is still the silicon keyword. It has been the case for the last 40 years. It's still the case. So prefer silicon-proven IPs to things you can do yourself when you can, of course. Yes, many system companies focus on their added value, which is the system really, and leave the rest to contracting company and so on. So important that. The last point, partnering with a trustable silicon design service, that is very often the right solution, both technically because you are engaging with people who are experts in doing SoCs, and financially because of what we said before. So it perhaps looks like a higher cost, but it's for a small period of time, as opposed to having to sustain a design center and many people and the A license for a long period of time, not with a very, very good utilization as well. Yes, I think this is the last one. Okay, thank you. Okay.
So thank you very much, David.
No problem.
It was a very good presentation, and also to summarize all this complex topic of design SoC in 1 hour and a half, but was a great overview for all the steps.
Thank you. No, thank you.
So we have some time for questions. I will start with
Do we have questions? We have a lot of questions from YouTube.
in the
Yes,
YouTube. Okay,
we
but I
do.
will start with one here.
Okay.
About like we are saying for the use and the importance of to have the silicon-proof IP. How do you see the chiplets in the market, and how you see the chiplet in the full SoC?
Yeah, no, they're definitely becoming more and more popular. Yes, they are increasing. That's what I can say. You need to have the right financial justification to move into chiplets. So he has to analyze the complexity of your solution and whether chiplet is the right methodology for you. But yeah, they are becoming more and more popular. Yes, that's right. The package design is going to be much more expensive, but it's becoming more popular. If that's the answer to your question, yes.
Okay, I have so many questions that I have to filter out some. I think that if you have any type of email or something that
Yes.
they can also forward you, because I don't think we will be able to answer all of them. They are very curious.
Okay.
All right. So the first question that I'm going to use here is how does the die size estimation is done? Are there any rules? Any rules of thumb to use die size estimation? This is from Thiago Maia Soto.
We need 1 hour for this.
Oh, okay.
Yes, the answer is yes. There are algorithms to translate complexities, functions into number of gates. Not very good accuracy, but what can you do? I mean, you have to make an assessment there. And you analyze your code, you assess how many adders, multipliers, memories, logic, and so on, and you come up with a number of gates and the number of memory bits for that block. And that's the beginning, because now we have to translate number of gates into silicon area. So you have other algorithms for doing that. And you have to translate number of memory bits into memory cuts, memory size. Then you have to consider utilization, because when you then map those, you make an assessment of how many chip area are needed for those thousands of gates. You need to consider the utilization of the backend tool. We have batteries, 60, 65%. It depends on the kind of blocks. When you put memories, you have to consider what is called the halo around the memories, because you cannot do nice routing or placement around those memories. Of course, it depends on how many memories and how we have to partition those memories, so the rules can change. You assemble everything together. We do it with quite a complex spreadsheet. Then important is to associate to every single IP in your system an accuracy factor, like an error range. So you say, because I've started from an RTL I've never seen before, for me, this estimation is plus minus 40%. Another IP, okay, no, this has been on silicon already, and when it was on silicon, you occupied 1.5 square millimeter. So for me, the range of error for this estimation here is plus minus 2%. Then you combine everything together, you come up with a die size at the end of adding everything, which is within a range that is under control. And then when you move throughout the flow, IPs, you start adding the RTL for those IPs, the gate level, and you improve the accuracy. And hopefully you will stay within that range. The range will decrease, and that's how you keep the die size under control. I'm not sure if I'm
a few minutes.
Yes, sorry.
All right. Okay, we have another question from Davide Santos. Could you please give us more details on how the costs are handled when third-party IPs are integrated into the design? Is it a one-time cost or a recurring cost based on product sales when you add third-party IP?
Okay, it depends on the IP vendor. I can tell you that the most popular model is a one-time cost. Certain vendors will also want a royalty on the volume. So, I don't know, an ARM CPU, for instance, it depends on which CPU. The expensive ones, they want you to pay a fixed initial cost. Might be $100K, might be even $1.5 million. It depends on the CPU. And then they ask you also 1.5% of the royalty, which of course depends on the volume. So you have to multiply 1.5% by the cost of your product, of your package die, which might be $20. That has to go to the IP vendor. Okay. But not always. Most of the time is one-off.
It's just a one-time,
yes.
one-time cost.
Yeah.
Okay, we have like 20 questions from Mauricio Carvalho. So I'm gonna, just say. What?
Isn't Mauricio working for ARM?
Probably. I'm not so sure. Actually, I don't know. Yeah. Okay. Okay. I'm gonna get one question from him at least.
Just to be clear, the 500K I mentioned before, just in case there is an ARM guy there, just made up numbers. Okay.
Okay. Yeah, that's good. That's good to know and good to start.
Yeah, totally made up.
I have so many questions, and they're all good questions. Okay. One of them is. How do you deal with telemetry and power management in silicon or software? Is it silicon or software managed, usually?
It's both. Telemetry, sorry, the other one?
Telemetry and power management.
Okay. It's both. So there are power management units in either on chip or off chip, and they can be software controlled as well.
Okay.
Short answer, I know.
Yeah. That was great. Okay, yes. I'm gonna go to Danielle now. Is time or money saved by first implementing, debugging, iterating the target ASIC functionality in FPGA, like the FPGA perspective, then refactoring a major design into ASIC?
Yes, it's definitely a good idea.
Yeah, I think it's even in your flow, right?
Possibly.
FPGA
Yes.
Okay.
No, actually, just to say a few words on that. We very often incorporate FPGA as part of our verification sign-off. Because again, silicon is not forgiving, bugs are very expensive, respin masks and so on. We have like two implementation paths. One is the main ASIC implementation path, and there is another one which is, the objective is to create an FPGA, if it's possible. Depends on the size. Sometimes it's not even possible. Sometimes you have to accept that a subset of your system goes into an FPGA. And you use that FPGA to run more extensive verification tests to minimize the probability of a mistake.
All right, and one question from Rafael for those, I'm not sure, I don't want to keep everyone here, so I'm gonna just have one more question. Could you comment on the distribution of digital and analog engineers inside a company like Ensilica, a typical SoC development team, how many analog and digital?
Okay, I can tell you the split within Ensilica, and it's 25, 70, 75?
25 analog.
25 analog to 75. But how many analog designers you need on a chip depends on the chip. There are chips which are heavily analog. The analog comes off and you have a small digital block surrounded by a large analog island. We do many of these actually. And you have the opposite. 90% is digital, you have just a PLL for analog. So it's impossible to give a, if I give you an average, it would be an average with a very big variance. So it doesn't have much meaning.
Okay, we have so many more questions, but if you don't mind, I'm going to share your email with them, so then you can
absolutely fine.
Questions.
No problem. I'll give you an email later. And,
yeah, I think it was very interesting. Exactly. It's just so everyone who is hearing us, who is on YouTube, it's basically his name, Davide.Sarta@ensilica.com. But I'll also share on our chat here. Thank you so much for this very interesting.
Okay, no problem. It was a pleasure. Take care.
Julio, do you have anything else to say? So we concluded this talk. Thank you everyone for participating.
Thank you guys.
Excuse me, David. First of all, thank you very much for the presentation.
Thanks to you. It's always a pleasure.
At the beginning of the presentation, you mentioned about a new team in Campinas.
Yes.
And I was interested in knowing if you are, if Ensilica actually is interested in opening, analog designers positions there.
In Campinas.
Yes.
We do have already analog designers, so the answer is yes.